framework to help the community develop general purpose agents using Minecraft as a kind of primordial soup. And MindDojo has three parts: a simulator, a database, and an agent. And here we designed a simulator API to unlock the full potential of the game for AI research. Like we support RGB and voxels as the sensory input, and you can do keyboard and mouse actions as output. And MindDojo can be customized at every detail. You can control the different terrains, weathers, and monster spawning. And it supports creative tasks that are freeform and open-ended. And for example, we want the agent to build a house, but it's the same question: what makes a house, right? It's impossible to use Python code, simple code, to define that you have achieved building a house. And the best way to do it is to learn through data so that the abstract concept of a house can be captured. And next, we collect an internet-scale knowledge base of Minecraft across three parts. The first is video, and because Minecraft is one of the most streamed video games online, we're able to collect 300,000 hours of videos with more than 2 billion words in English transcript. And we also collected Minecraft wiki pages with more than 7,000 pages, and then the Minecraft forum as a subreddit where people go there and use it as a Stack Overflow to ask for help. So here's a peek at our MindDojo wiki dataset. And can you believe that someone listed all the thousands of recipes in Minecraft, page by page on this wiki? They just have a lot of time to kill. But I'm not complaining. Do more, because it's all data for our models. So please do more. And now, how to train this foundation model, how to use the data that we collected. We have a very simple idea in the original MindDojo paper. So for our YouTube dataset, we have time-aligned video clips and transcripts. And these are actually real tutorial videos. Like here in text prompt 3, as I raise my axe in front of this pig, there's only one thing you know is gonna happen, right? Some YouTuber actually said this in the tutorial. And now, with this time-aligned video and text, we can first train a pair of encoders to map the video and the transcript to the vector space. And then we can train embeddings by contrastive learning, which is essentially pulling together the video and text that match and push apart those that don't match. And this pair of encoder model is what we call the MindClip model, based on the idea of clip from OpenAI. And intuitively, MindClip learns the association between the video and the transcript that describes the action in the video. So it outputs a score between 0 and 1, where 1 means perfect description, and 0 means the text is irrelevant to the video. And now this essentially becomes a language-prompted foundation reward model. So let's see MindClip in action. Here's an agent interacting with the simulator. The task is written in natural language. It's called shear sheep to obtain wool. And as the agent explores, it generates a video snippet, which is then encoded and sent to the MindClip model to compute a score. And the higher the association is, the higher the score is, the more we know that the video, the actions of the agent, is aligned with the text instruction. And that becomes the reward function to any reinforcement learning algorithm. And this looks familiar to you. If this looks familiar to you, that's because it's essentially reinforcement learning from human feedback, or RLHF in Minecraft. And RLHF is the cornerstone algorithm that made ChatGPT possible, and I believe it's also going to play a big role in building generalist agents. And then we see that the model can generalize also zero-shot to different weathers, lighting conditions, because it's been trained on internet data. And here are some demos of our learned agent behavior on various tasks. Now, let's put MindClip on the map. It's able to do a lot of tasks, but the limitation is that you have to manually decide a task prompt and then run training every time for a different prompt. And the agent isn't able to discover new things to do. So, can we do better? And we did do better in 2023 when GPT-4 came, a language model that is so good at coding and planning. And so we built Voyager, an agent that massively scales up on the number of skills. And when we set Voyager loose in Minecraft, it's able to play the game for hours on end without any human intervention. And here, this video is a single episode of Voyager, where it explores the terrain, mine all kinds of materials, fight monsters, craft hundreds of recipes, and unlock an ever-expanding tree of skills. And how are we able to do this? The key insight is coding as action. So we convert the 3D world into a textual representation thanks to a Minecraft JavaScript API, open source, by the community. And Voyager invokes GPT-4 to generate a code snippet in Minecraft. And each code snippet is a skill. And yet, just like human engineers, Voyager isn't always able to get this right on the first try. So we have this self-reflection mechanism to help it improve. And there are 3 sources for self-reflection: the JavaScript execution error, the agent state, like hunger and health, and the world state, like landscape and enemies nearby. And once a skill becomes mature, Voyager will store the program into a skill library. And you can think of the skill library as a code base, authored entirely by GPT-4 through trial and error. And in the future, when Voyager faces a similar situation, it doesn't have to redo the trial and error again. It just retrieves the skill from the code library and execute it. And in this way, Voyager bootstraps its own capability recursively as it explores in Minecraft. And a question still remains: how does Voyager keep exploring indefinitely? We give Voyager a high-level directive that is to find as many unique items as possible. And then Voyager itself implements a curriculum to find progressively harder and novel challenges to solve. And putting all these together, Voyager is not only able to master, but also discover new skills along the way. And for the skills I show here, we didn't program any of this. It's all Voyager's idea. And what you see here is called lifelong learning, where an agent is forever curious and forever pursuing new adventures. And here are 2 bird's eye view of the Minecraft map. And the biggest orange circles are the distances that Voyager travels compared to many baseline methods. And because it likes traveling so much, and that's why we give it a name, Voyager. Compared to Minecraft, Voyager is able to pick up a lot more skills. But still, it only learns how to control one body. So can we scale on a different axis and have a single model that works across different body forms? And that enters Metamorph. It is a project that I co-developed with Stanford researchers. We created a foundation model that works on not just one, but thousands of robots with different arm and leg configurations. And Metamorph has no problem adapting to extremely varied, physical structures of these robots. So here's the intuition. We develop a vocabulary to describe the robot body parts. And then each part now becomes a sentence written in this language of the robot body. And more specifically, we can express each kinematic tree into tokens. We can convert those into tokens. And then the sequence by itself as a sentence will describe the morphology and kinematic properties of the robot. And now you can have different robots that have different numbers of joints and configurations, but the tokenizer doesn't care, right? It's all converted to tokens. And then what's the knee-jerk reaction from AI researchers? We see sequences, we reach for a transformer because attention is all you need. So we apply a big fat transformer to control these robots. And this transformer is called Metamorph. But unlike ChatGPT, which writes out text, Metamorph writes out motor control for each joint in the body. And because we want to learn a universal policy that works across morphologies, we batch together all the robot sentences and then train a big multitask network. And whatever the robot will look like, it's always going to be compatible with each other, because at the end of the day, it's just a sequence written in a different language. And then we just train these in parallel using reinforcement learning. So we teach the robot to walk through flat terrains, complex terrains, and also navigate obstacles. And in our experiment, we see that Metamorph can control thousands of different robot forms. And more interestingly, it's able to generalize to robot forms never seen during training. Now, let's extrapolate into the future. If we expand the robot vocabulary to include more complex configurations, then I envision one day that Metamorph 2.0 will be able to generalize to robot arms, dogs, different types of humanoids, and even beyond. And compared to Voyager, Metamorph takes a big stride towards multi-body control, and now it's time to take things to the next level and transfer skills across the boundaries of realities. Enters Isaac Sim, NVIDIA's simulation initiative. Isaac Sim's greatest strength is to run physics simulation at 1,000 times or even more faster than real time. And here you see our 1,000 robot hands training in parallel. And this character learns these impressive martial skills by going through 10 years worth of intense training in only 3 days of GPU compute time. So this is very much like the sparring dojo, the virtual dojo in the movie Matrix, and we're doing this in reality. And this race car scene here is where simulation has crossed an uncanny valley. Thanks to hardware-accelerated ray tracing, we can now render very complex worlds with breathtaking levels of details. And the photorealism here can help train computer vision models that will become the eyes of AI agents. And what's more, in Isaac Sim, we can procedurally generate infinite worlds, and no two worlds will look the same. And here is an interesting thought. If the agent is trained on 10,000 different simulations, they may as well just generalize to the 10,001st reality, which is our physical world, and just let that sink in. Now, what new capabilities can this fantastic view simulation tool unlock? This is Eureka, an agent that achieves robot dexterity at superhuman level. Well, perhaps not all the humans, at least better than me. So you see the pen spinning here. I have given up on this task for a very long time since my childhood, but apparently the robot I trained can do this better. So the idea is Isaac Sim has a Python API to construct the training environments, like this 5-finger robot hand. And we also assume that there is a success criterion. For example, we can check if the pen has reached a specific 3D orientation, so the task is successful or not. And with these, the first step of Eureka is to pass the environment code and the task description as context to GPT-4. And the task here is written in natural language to make the hand spin the pen to target positions. And then Eureka samples a reward function, which is basically a very fine-grained signal that teaches the behavior of the neural network towards a good solution that you want. And normally, this reward function is engineered by humans, and actually expert humans who are very familiar with physics simulation. And this is a very tedious and difficult process. And now, Eureka can automate it. And once we have the reward function, we'll run reinforcement learning to maximize it through lots of trial and error. And it only takes 20 minutes to finish a full training run. And putting it together, GPT-4 will generate a bunch of reward function candidates, and each will perform a full reinforcement learning training run. And then Eureka will pass on the automated feedback and ask the language model to self-reflect on the results so it can propose better reward functions to better solve the problem, and rinse and repeat. And you can think of it as a kind of in-context evolutionary research. So compared to expert humans, we actually found that Eureka can even outperform some of the experienced NVIDIA engineers who wrote Isaac Sim. And you see here, it can spin the pen. It can teach the robot hand to spin the pen along different axes, right? You can even spin the pen in reverse, right, when gravity is against you. And these are really hard. I wrote reward functions before, I want to pull my hair out. But Eureka is able to discover different reward functions for each of these tasks. And then we did all the first paper in simulation only. The next question is, how do we transfer from the sim to the real world? Here, there's an idea called domain randomization, which is basically the idea that if you train in 10,000 different simulations with different gravity, friction, object weights and size, and it may very well just generalize to our real world, because the real world now is part of your simulation. And this is what we do. This is the old Eureka. And we simply ask GPT-4 to also sample the domain randomization configurations for us, and then in the hope that it can transfer to the real world. And it does transfer. So here on the left-hand side, it's a simulation of the robot dog running forward, and we're able to zero-shot transfer to the real world. And that's a real robot dog also running forward. And this is a hand rotating cubes, and that's a hand rotating cubes in the real world. We did not do the pen spinning in the real world, because actually, not the algorithm is okay, but the hardware is a limiting factor. There's actually no real 5-finger hardware hand in the world that can have so much force and agility to spin a pen. So we're still waiting for the hardware providers to catch up with Eureka. And this is the most impressive demo we showed. We trained a robot dog to walk on a yoga ball in simulation, but we cannot really simulate the bouncy, the deformable yoga ball in sim. So we just randomize, and Eureka is able to find a very good solution, so we transfer to the real world. And this is my collaborator from UPenn, walking the robot dog there on the street, an episode right out of Black Mirror. And because it's using domain randomization, DR, we call it Dr. Eureka. And it's worth noting that Eureka is a general purpose method that bridges the gap between high-level reasoning and low-level motor control. So Eureka uses this paradigm that I call hybrid gradient architecture, where an LLM writes a reward function, and that's high-level reasoning. And the reward function instructs another smaller neural network using reinforcement learning. And this is the dual loop design that we use and leverage the help of LLM to train robots. And Dr. Eureka just changes the reward function and add the sim to real configuration. And I envision someday that Eureka++ will be able to just program the task, the embodiment, and even entire simulations for me, so that I can go on a vacation someday. And then Eureka++ will do all the development for me, automate the entire robotics pipeline. And then when I come back, I have trained the robots. And don't tell Jensen that. So in this sense, the Eureka work isn't really a point on the map, but it's a force vector that can push the frontier along any axis, because it's a general purpose algorithm that simply does coding. And as we progress through the map, we'll eventually reach a single model that generalizes across all three axes. And I call that the foundation agent. And that's the upper right corner, the ultimate destination through our hitchhiking across the galaxy. And I believe training foundation agents will be very similar to ChatGPT, right? All language tasks can be expressed as languaging, as texting and text out. And ChatGPT simply trains it by scaling it up across lots and lots of text. And very similar here, the foundation agent takes as prompt an embodiment specification and a language instruction, and then it outputs actions. And we simply scale it up massively across lots and lots of realities. And the foundation agent is the next chapter for our Gear Lab. So I know I'm running out of time here, and I will quickly go through the last one, the one more thing, which is that in March, Jensen announced Project Root at NVIDIA GTC keynote. And it's a cornerstone initiative on our roadmap. The mission is to create a foundation model for humanoid robots. And this is a scene from Jensen's GTC keynote, where a lot of our humanoid robot partners showed up on stage. And why humanoid? Because it is the most general purpose form factor, right? The world is designed around the human form. All our tools, equipments, and houses restaurants, they're all designed for humans. And in principle, given a good enough humanoid hardware, it should be able to do anything that a reasonably untrained human can do. So we just aim for the most general purpose hardware there. And why do it now? Because we see the manufacturing cost of humanoid robots dropping exponentially over time. In 2001, the NASA humanoid cost north of $1.5 million. And just 2 weeks ago, Unitree announced their G1 robot that will only cost $30,000. And that's roughly the price of a car. And the manufacturing cost of mature products will tend to approach the cost of the raw materials. And for the humanoid robots, they only take 4% of the metal that's required to build a car. So in principle, the cost can even go down further. And here I just want to show a snippet from Jensen's keynote. And this is the view of my lab, the lab I work in. It's called the Gear Lab. And these are the 4 humanoids that partnered with us for the GTC keynote. And so the fun story was one of our partner companies, they drove a car here with a trunk full of body parts. Because the humanoids break so often, right? They're still quite brittle. So they changed like 3 different hands and 2 heads during the demo. And it's just a bag of body parts. And computer scientists are the creepiest people on earth. And this is one of my favorite pictures from GTC. It's taken in front of NVIDIA's headquarters. And by the way, NVIDIA headquarters is called Voyager. I wonder why. And here we see Actronic, Fourier, Agility, and Unitree, the 4 companies. And just look at how happy these new species of humans are there. And on the high level, we're building the GR00T model to take as input multimodal instructions and then be able to control a humanoid robot in a loop. And here I will quickly show some demo where this is a video instruction. And this is the GR1 robot from Fourier Intelligence imitating the human from a raw video and dancing, and it's able to keep balance. And this is the GR00T model learning from a human teleoperated demonstration trajectory. And we do cold press juicing. Yeah, and we did a lot of cleaning. A lot of cleaning, you can't believe it. And of course, we'll use simulation, right? Before NVIDIA was an AI company, it was a graphics company. So simulation is actually our stronghold. So we use Isaac Lab to run lots of different environments and tasks for the humanoids. And we train different kinds of humanoids in this massively parallel simulation where 3 days of time is equal to 10 years. And we hope that those that are trained in simulation will transfer to the real world. So back to this question, what makes a cat a cat? The most profound question ever. And what does this mean in the agentic era? Well, we don't have any robots that even approach cats in their agility, right? Cats are these embodied agents that are phenomenal in their sensory motor loop. They're so reactive and even faster than humans. And that does so well, right there. So can we have robots someday to be as good as cats? Or even better, can we have humanoid robots pet the cat for you? Right? Feel its fur through the tactile senses on the fingers, adapt to the cat's movements, and even sense its emotions, right, through vision and sound. So that one day our humanoid robots will continue to serve our cat overlords on behalf of us humans. Now zooming out, I believe in a future where everything that moves will eventually be autonomous. And Project GR00T and humanoid robots are only the first chapter. And one day, we'll realize that the agents across WALL-E, Star Wars, and Ready Player One, no matter if they're in the physical or the virtual world, will just be different prompts to the same foundation agent. And that, my friends, is the North Star on our quest for AGI. And I welcome you all to join me in the agentic era. Thanks.